Hello guys, welcome to ITU Physics channel. Today let's do a quick revision on free body diagram, which is very important when we solve problems that are related with forces. First of all, let me explain the types of forces that we are going to encounter, or at least important for IB or advanced level physics. The first one is tension. So what's tension? A tension is a force that originates in a string or in a body when it is stretched. The reason behind this force can be actually explained by electromagnetic interactions between the molecules of the material. For example, look at this diagram. A small mass M is attached to a string and that is connected to a ceiling. In this case, there is a force, a tension force acting on this mass. In all the cases, whatever the things we are discussing here, we assume the string has no mass. So this is one of our assumption, massless string. Massless string. So if a small m is connected to a massless string, the mg is the weight of this object, so which is downward, and this system has to be at rest. So to be at rest, there should be an upward force acting on this body. So if you take this body separately, only there are two forces acting on the body. One is downward weight and the other one is upward tension. We say the string has no mass. More precisely, it is actually the mass of the string is very small compared with the system actually we are discussing, the masses of this one. Therefore, we used to neglect the mass of the string. And similarly, look at this, a pendulum at an arbitrary position. Mg is downward always, and this T represents the tension on this body. And similarly, look at this one. A string is actually kept over a pulley and connected to masses M1 and M2. So these two masses again will experience a tension force. Always the weight of these two masses would be downward, so M1G and here M2G, and because of this string there would be a tension force. So if you take this object separately, there would be a force like this, M1G downward and tension upward. Similarly, if you take this object separately, there would be a force like M2G downward and upward tension T. So this is we call tension force. Similarly, let's take this one. Here again mg would be downward and upward T, the tension force on the body. So this is actually these are the total forces acting on the body. And if you take our string, let's take for example this string. If you take the string, the forces would be like this on the string, and this is actually I have drawn here on the body, and this would be on the string. Now let's move to the normal forces. So normal force originates when one body touches the another body, and this force is always perpendicular to the touching surfaces. For example, just imagine if a box is kept on a surface, we agreed there would be a downward force, that is our mg, and there would be an upward force, that is we call a normal force, that would be completely upward to this force, and we know the entire system is at rest, so we can say this R, this reaction force, should be equal to mg. And similarly, if you keep the box on an inclined plane, this is how you need to mark. The mg is always downward. Now the normal force would be, I said it should be perpendicular to the touching surface. So this is the surface that touches with this object. So the reaction force or the normal force should be perpendicular to this surface. So meaning this should be 90 degree. And let's look at the next example. So in this case, a ladder is kept on a surface and the other end touches a wall. So even in this case, this would experiences a normal force, or we can say reaction force. So you see this part of the ladder touches this this portion of the ground, so there would be a normal force upward, R2, and this would be completely perpendicular to this surface. And similarly, look at this part of the ladder is actually touching this surface. So the surface will give a force on the ladder that is perpendicular to this touching surface. Let's call this as R1. And also you see the mg is, we know there is always the weight. This is how the weight of the ladder. And also remember there should be a frictional force on the surface, so that the friction would be not this way, the friction would be in the opposite direction. Okay, because then only we can say if the system is at rest, this R1 force should be equal to this F, and we can write down the second equation as this R2 should be equal to mg, right? Because you see all the horizontal, the vector components. So this side we have F, the frictional force, and here we have the reaction force. So F definitely should be equal to R1. And if you take all the vertical forces, we have upward R2 on the body sorry, and the downward mg, so R2 should be equal to mg. Okay, so let's move to the drag forces. So what is drag force? if an object travels through a fluid, meaning it could be gas or liquid, experiences a force that opposes its motion. So these are known as drag forces. For example, air resistance is a good example for drag forces. So look at this one. This diagram shows motion of an aircraft. So if the aircraft moving this way, there would be a drag force which actually opposes this motion. And the next one is upthrust. So the objects that are floating on a surface of a liquid experiences an upward thrust, or we can call this as buoyancy force. Buoyancy. Sorry. Buoyancy force. So you see, if an object is floating on a surface of a liquid, we usually denote it by this upward thrust as U. So if the system is at rest, we can say this U must be equal to mg. That is clear. And you see, what is actually U? U is a force which is acting upward, and this U can be written as volume V, the density of the liquid, multiplied by the gravity. So what is this V? Because rho is known, rho is the density of the liquid, and what is this V? V is the volume that is inside the liquid. So for example, in this case, the volume inside the liquid is this small portion. So you need to find the volume of this one, and you need to multiply the density of the liquid and G. This should be equal to the mass of this body. And similarly, in this case, how do you write down the equation? This U should be equal to mg inside the liquid if it is at rest. What is actually U now? You should write down V, density of the liquid, G should be equal to mg, and this V now, you see, the complete volume of this body, because the total volume inside the liquid is now this complete volume. So in this case, you have to put the complete volume of the body. So the next one is frictional forces. We all actually familiar with this, with the idea of friction. So this is a force that is created whenever two surfaces move or try to move across each other. Or meaning of this, simply, if there is any relative motions between two surfaces, you will observe a frictional force. So similar to other forces, even the frictional force always opposes the motion, and the friction actually depends on the surface. So depending on the surface, the frictional force will change. And so if you take, for example, this one, a mass is moving this way, the mass moving this way, these are all the forces acting on the body. Mg is the downward force, R is the normal force we discussed just now, and if this object is moving this way, the frictional force should oppose this motion. So the friction should be marked in the opposite direction. And similarly, if you take this one, a box is kept on an inclined plane which makes an angle theta degree. So if you keep it, it starts to move downward. So if the object move downward, there would be a friction upward. So the friction is always opposing the motion. And let's move to the last part of this tutorial. So the last part is, this is our main task. Free body diagram. What is a free body diagram? A free body diagram can be used to represent all forces acting on the body. So this is really important when you solve the problems that are related with forces. For example, now you already have some ideas about how to mark forces acting on the objects. So let's assume a small mass is hang from a string. And how do you mark all the forces acting on the body? Is simply the downward mg and the upward tension T. And in this case, how do you mark all the forces acting on the body? The downward force mg, and there is a normal force. How do you mark this normal or the reaction force? You have to mark such that it should be perpendicular to this touching surface. Okay, you need to mark like this. Okay, it should be 90 degree. It should make a 90 degree. Okay, and similarly, if you take this one, this is, let's say, a circle. A small mass m is actually rolling along this surface. So how do you mark the forces acting on the body? The first one is downward mg, and you see now this is our surface that actually touches with the body. Therefore the reaction force would be, or the normal force would be normal to this surface. Oh, it should make 90 degree with the surface. So if I draw a tangent line, so this is our tangent line, this should be 90 degree. Let's do some exercise. So how do you mark all the forces acting on the system? First, let me mark mg is the downward force acting on this body due to gravity, and this is a string, so there should be an upward force T. So these are the only forces acting on the body. And if you take this small mass, there would be a downward force mg, and there would be an upward force, the normal force we say, which is equal to R. Since this is attached by a string, there should be a tension force on the body. And let's assume this surface is a frictionless surface. If there is no friction, you don't need to put any frictional force, or otherwise you have to mark even the friction. Okay, I'll put small f. So these are the forces, all the forces acting on this mass, and these are the forces acting on this small mass. Let's do the next problem. So in this case, let's say here there's a small string, a ring, okay, and this object is connected by using 3 strings. Okay, so this is a first string, second string and third string. How do you mark all the forces acting, for example, on this small m? The first you have to mark mg, that is our weight of the object, and upward should be a tension T. Okay, I'll mark this as T1. So these are the forces acting on this body, okay, on M1. How do you mark all the forces acting on this ring? So this is our ring. Downward there should be a T1, okay, because here there is a T1 force, so this side in the opposite direction there should be a T1, and this is a different string, so I can't actually use same T here. Here remember we use everywhere same T because this is a one complete string, therefore I use same T, but here that is not the case. So let me put here T2 acting on this string, so I have to put here T2, and let me say these are not same angles, okay, let's put alpha beta. So here we have another force, let's say T3, okay, on this string. So these are the forces acting on the ring, and this problem we already discussed. How do you mark all the forces acting on this ladder? The weight of the ladder, and here there would be a reaction force, let me call R1. Here there would be another one, I'll call R2, this should make 90 degree, and here there would be a frictional force F. So these are the forces acting on this ladder. And if you take this problem, mg is downward. If you give a force, okay, to pull this object, there would be an upward force R, that is the reaction force, and if there is no friction, you don't need to worry about frictional force, otherwise you need to mark a frictional force that should oppose this motion. So this is the idea about free body diagram, and finally let's discuss about Hooke's law. So what is Hooke's law? Hooke's law says force proportional to its displacement but in the opposite direction. This law can be applied only under the elastic limit. If your spring go away from the elastic limit, this law cannot be applied. So only you can use this law if your spring is under the elastic limit. So I can say force proportional to minus x. It's saying the force proportional to the displacement but in the opposite directions. So I put a minus sign here. If you know this, from here I can say F is equal to minus kx, and we introduce a constant. This constant is known as spring constant, and the unit of this spring constant is Newton, meter minus 1. And I'll explain why there is a minus sign here. Imagine the spring. A spring is connected, let's say, to a wall, and let's assume this is your reference point. Okay, so you measure the distance from here. This is our positive x-axis. So here x equal to 0. If there is a force on this spring, there would be another force that oppose this that is opposite to this spring.